right, in this section, we're going to now tie together what we know about computing total head, pressure head, elevation head, and so forth with effective stresses, because that's the ultimate goal here. In soil mechanics, the reason why we care about these head values is largely because of stability issues. How is the excess pore pressure going to influence the strength of the soil? And that's related to effective stress. So the key concept here is that fluid flow induces seepage forces that alter the effective stress in the soil. Okay, we already know we can't just compute pore pressure based on a hydrostatic assumption when there's flow. So we need to compute the flow first, and then it's easy. You already know how to get total stress, integral of unit weight with depth. Now you know how to get pore pressure, right, from the seepage analysis, and the effective stress is still just total stress minus pore pressure. So let's do a quick example here. What we're going to do now is compute a few extra things, right? We're going to compute total head, pressure head, and elevation head for this problem. But then we're going to take it a step further and transfer those results to compute pore pressure. And then we're going to compute vertical total stress and vertical effective stress. And we're going to do all of this at points A, B, and C here within this soil layer. So we'll assume that the unit weight of water is 10 kilonewtons per meter cubed here instead of 9.81, just to make the calculations a little bit easier. So what we have is a condition where there's a water table on the left side, a water table on the right side, and then there's soil down here, and we'll assume that the soil is supported at the bottom so that it's not free to just fall out of this device, and we're pushing water basically from the left through the right side. And we're going to solve it for two different groundwater cases, right? Case one has the water right at the same level as on the right side. The left side and right side are the same. Therefore, it's hydrostatic, right? There's no flow going on here because there's no hydraulic gradient through the soil. Then we're going to solve for case two, which is where the water gets raised up 2 meters on the left side. So let's do case one first. This is kind of a review, but I just wanted to show you how to get it in terms of the context of our seepage problem. So let's talk about what we know. At points A, B, and C, we know the elevation head. Okay, we always know elevation head. At points A and B and C, those are right on the boundary of a soil layer, so there's just water between that soil surface and a free water surface. Therefore, we know the pressure head at those points. So at point A, we're going up to this water level. It's 2 meters, right, between point A and the water surface, so the pressure head is 2. At point C, we're going around this way and up, so we have to go up 5 meters and then up 2 more meters, so it's 7 meters of pressure head there. And now we can calculate the total head. It comes out to be 0 for both cases, right? Just because of where we chose the datum, right at the free surface right there. Okay, now what we can do is interpolate the total head at point B, just like we've been doing. Point B is directly in between A and C. The soil has a uniform hydraulic conductivity, therefore we can just take the average. So the average of 0 and 0, of course, is 0. And then we can calculate the pressure head, and it comes out to be 4.5, right? Okay, now the trick is that we can compute pore pressure from the pressure head. All you have to do to get there is multiply the pressure head by the unit weight of water. So here the pressure head is 2 at point A, therefore the pore pressure is 20 kPa. Note that we're going from meters to kPa just by multiplying by gamma W. At point B it was 4.5, so we get 45. At point C it was 7, so we get 70 kPa of pore pressure. Now the total stress, this is actually a little bit tricky. Students often forget to include the water that's up above the soil. Total stress, you're always going to integrate from the downward from the free surface where there's air. So that's either going to be a soil air surface or a water air surface for submerged soil. The problem students often make is that when there's water above the soil, they integrate from the soil-water interface down to get total stress, but you can't do that. You need to go all the way up to the top of the water because there is some pore pressure at point A. right? So right at the ground surface right here, we know the effective stress is 0. The water pressure is 20 kPa. Therefore, if the effective stress is 0, the total stress must also be 20 kPa, right? That's one way to think about it. So anyway, we're going to integrate unit weight with depth from the water surface down to each point. At point A, that's 20 kPa. At point B, it's going to be 20 kPa plus 2.5 meters times the unit weight of the soil. So 20 kilonewtons per meter cubed is the unit weight of the soil, so you get an extra 50 kPa. So here it's 70, and then at the very bottom at point C, you get 120 kPa for vertical total stress. And then we can calculate our vertical effective stress just by doing the subtraction, right? 20 minus 20 is 0. 70 minus 45 is 25, and then 120 minus 70 is 50. So we've solved the problem. That's an easy problem because there was no seepage, but I just wanted to show you the process so that you can easily compute a closed form solution and make sure it agrees. All right, now with a 2 meter rise in water, that's case 2, the elevation head stays the same. The pressure head at point A stays the same because we haven't done anything with this water, so point A is still controlled by the water on the right. But now the pressure head at point C has changed because it has to come down here and go all the way up to that surface. So we've added 2 meters to the pressure head now. So instead of a 7, we have a 9 in there. And that means that the total head is 2 at point C, right? We do total head is equal to minus 7 plus 9, it's equal to plus 2. Okay, now we have to linearly interpolate the total head at point B, and so we get 1. Very easy linear interpolation. And then the total head, the pressure head is equal to the total head minus the elevation head, so you end up with a 5.5 in there. Notice if you sum up elevation plus pressure, you get 1, so it all works out. Okay, now we can compute pore pressures. They go up a little bit. So, well, they go up a little bit at point C and B. So you still have 20 at point A because the water table hasn't changed there. Now you get 55 at point B and 90 at point C. The total stresses stay the same because, again, we were integrating unit weight down from here to get total stress. Nothing has changed on that side. So sigma V stays the same. Now sigma V prime has gone down, right? We have 0 and point A, and then instead of 25 at point B, we have 15, and instead of 50 at point C, we have 30. So by flowing water upward through the soil, we've decreased the effective stress, which means that the soil is now weaker. So if we were to plot these things with depth, for case 1, here's sigma V prime, this is U, and this is sigma V, just plotting the points. For case 2, here you have sigma V prime, U, and sigma V, right? So that's a nice way to present these results. Okay, now what if the water table was raised up 3 meters more on the left side? Okay, we've already raised it 2 meters, and we saw that the effective stress decreased. Well, let's see what happens if we raise it 3 additional meters. So now the pressure head at point C is 12 meters, right? It started at 7, but we've raised it 2, and then we raised it an additional 3, so it's gone from 7 up to 12 meters. The elevation head is -7, therefore the total head is 5. All right, and then we can linearly interpolate the pressure, the total head at point B, and it's 2.5, so the pressure head is 7 at point B. Okay, and when we calculate pore pressure, we get 20, 70, and 120 for those pore pressures. That's exactly equal to the vertical total stress. So what we end up with is a case where the effective stress is 0 at all 3 points. And if we plot our vertical profiles, we have the total stress and the pore pressure. Vertical total stress and pore pressure are identical to each other, so the black and green lines are on top of each other. The blue line is all zeros. All right, so this condition creates quicksand. This occurs when the upward seepage force is large, such that the pore pressure is equal to the vertical total stress. We'll talk about what that means in just a second, but if you have a material that's cohesionless, just loose particles of sand, let's say beach sand, that are kind of stacked on top of each other, and you push water up through it. Basically, the sand particles are fully supported by this upward seeping water. The seepage force is large enough to balance the downward force of those particles, and they're not really touching each other anymore. So you've created this quicksand condition where the soil basically has no strength.